Hi, it's Mr. Baker here with another physics video. Today we're going to be looking at magnets and magnetic fields. So today we're going to be looking at magnets and magnetic fields, and we're going to be answering this question: why is some stuff magnetic? Okay, so I'm sure you've all played around with magnets before, and you will have found out these things, I'm sure. So when you've got two magnets, and you've got a south and a north pole, so you've got unlike poles together, what's going to happen? Exactly. So they're going to attract, aren't they? So when you put those two together, that's what's going to happen. When you've got two magnets where you've got the same poles, they repel. The further away you put those magnets, the less likely it is that they'll do anything. So what we can say is that like poles repel, unlike poles attract, and the closer the magnets are, the stronger the force. And you'll find those things out from just playing with some magnets. So what do we call magnetic materials then? So here we've got lots of different metals, but are they all magnetic? Well, no, they're not. There are only very specific metals that are magnetic. And actually, if we put a magnet next to a load of metals like this, we would find that iron, nickel and cobalt are magnetic. We call these ferrous materials, and all other materials are non-ferrous. Now we're going to see what magnetism is and how we magnetize things. We've got two different magnetic materials, and you can see that they're magnetic materials because they've got these little bar magnets here, which are kind of showing us what the domains are like. Now, domains are what we think of as small portions inside a ferrous or a magnetic material that we can line up. Now, this is to do with the spinning of the electrons inside the material, and if we can line those up, then something will be magnetic. You can see we've got some piles of pins underneath these, and with these piles of pins, we're going to indicate whether the thing is magnetic or not. So let's lower this magnet first of all on the right hand side. And this is one of the ways that we can make something magnetic. We can induce a magnetic field by putting something that is magnetic near to it. And you can see that what happens as I move that down is that those little bar magnets, those domains, line up, and this material has become magnetic. Now let me do the same with the one on the left as well. So you can see that as we bring the magnet towards the magnetic material, the domains line up, the pins are attracted to it, and there we go. So we've aligned these domains, and we have made both of these materials magnetic. What's the difference? So if I move my magnet away from this one on the left, you can see that this material stays magnetic, whereas if I move the magnet away from the one on the right, it doesn't. And so this is the difference between something we call soft and hard magnetic materials. This would be something we'd call a hard magnetic material, something like steel, which keeps hold of its magnetic field once the thing that's induced the magnetism in it has been removed. Whereas this is a soft magnetic material, it will lose its magnetism as soon as the thing that's induced the magnetic field in it has moved away. So we've had a quick look then. So what makes stuff magnetic? So all objects are made of atoms, as you know. Atoms have a nucleus surrounded by electrons. The microscopic ordering of electron spins that ferromagnetic materials have leads to regions of magnetic alignment, which we call domains. When you put a ferrous material with domains in a magnetic field, they can be lined up, making the material magnetic. When electric current flows through a conductor, it has a similar effect. Materials like iron would be described as soft magnets because as soon as it exits a magnetic field, the domains point in random directions again, and so the material becomes demagnetized. Materials like steel can be made into permanent magnets and can be described as hard magnets because the domains will stay lined up. So one of the things that we might want to do is to draw the field lines around a magnet, and we can do that really simply if we've got a plotting compass like this. So a plotting compass will point towards the North Pole, and if we have a magnet near it, then the south end of the pointer will be attracted to the North Pole of the magnet, and so we'll get something like this. So when we put it in a straight line away from the North Pole, we'll get this line like this. And you can see I've drawn an arrow, and I've drawn that pointing away from north, and this is how we draw magnetic field lines. The magnetic field lines always go away from north and towards south. So I would have a line like this. If I took my plotting compass again and put it somewhere like this, I might get it pointing in a direction like this. So the way that I would do this is I would put a little point just there and just there with a pencil, I would move the compass, and I'd do the same thing again. Put a little dot there, put a little dot there. And I would keep putting dots on my plotting compass all the way around. And then I would draw my line. So I'd basically join up the dots. And I'd put an arrow going from north to south. And if you keep on doing that, then you'll end up with something that looks like this. So we can see the magnetic field around a permanent bar magnet here. There's something else we can see. We can also see the strength of the magnet. So we can see that the magnetic field goes from north to south, and that's shown by all of those lines. We can see the field, we can see the pattern of the field. We can also see the strength of the magnetic field by the density of the lines. So where there are lots of lines, like at the poles, the magnet is strong. The further away you are from the poles, there are less lines going through the same area, and so the magnetic field is less strong. If you put two magnets together, then you might get patterns that look like this. So on the left-hand side, we've got two bar magnets with similar poles that are close to each other. So north and north pointing towards each other. And we get this field pattern. And we also get in the center between the north poles there, we get a region where there is no magnetic field at all. On the right-hand side, we've got a diagram where we've got north and then south close to each other. And we get field lines that look like this. And you can see that the field lines are always going from north to south. You can see that the Earth's magnetic field looks like a bar magnet's magnetic field. So what causes the magnetic field around Earth? Inside the Earth is liquid iron, which is flowing due to convection currents and the spin of the Earth. The flow of the iron generates electric currents, which produces magnetic fields. Okay, so now I'm going to blow your mind. Some people never recover from this, so I hope you're ready. Are you ready? Okay, well, let's see. The North Pole is actually the South Pole. What? Okay, let me explain. So the north end of a compass is the north pole of a little permanent magnet. As we know, the north pole of a magnet is attracted to the south pole of another magnet. So for the north end of the compass to point in the direction it does, it must be attracted to a strong south pole. So the north pole is actually the south pole because it's attracting the north end of the compass to it. We just call it the North Pole because the north end of our compass points to it. You got it? Okay, well, maybe have a rest and come back to it. Maybe listen to this again, see if you can work it out. Okay, so that's the end of this one. These are the things you should be able to do. You should be able to state the names of the poles of a magnet and describe how they interact. You should be able to list some magnetic and non-magnetic materials. You should be able to sketch the shape of a magnetic field around a bar magnet and describe how it can be investigated. You should be able to compare the Earth's magnetic field to that of a bar magnet. You should be able to describe the regions in a magnetic field where magnetic forces are greatest using the idea of field lines. And you should be able to explain how magnetism can be induced in some materials. Okay, so this was our lesson on magnets and magnetic fields, and we asked at the beginning, why is some stuff magnetic? Well, it's all down to the domains. Ferrous materials have domains which can line up. When these are lined up, then the material will be magnetic. If that can't happen, then the material won't be magnetic. Okay, so I've been Mr. Baker. This has been another physics video all about magnets and magnetic fields, and I'll see you next time. Thanks very much.